Welcome to this lecture on testing means. Imagine you buy a bag of coffee that claims to weigh exactly 250 grams, but you suspect it is lighter. How can you prove it without weighing every single bag in the world? Today, we will learn how to use a small sample to make confident, mathematically sound decisions about an entire population. To begin our investigation into testing means, we must first establish a baseline assumption, which we call the null hypothesis. This hypothesis usually states that everything is completely normal and the true average of the population is exactly what the label claims it to be. We then take a small random sample and calculate its average. Testing means is the rigorous statistical process of seeing if our sample provides enough mathematical evidence to reject that baseline assumption in favor of our suspicion. It is the foundation of how we separate real effects from random noise. Now that we understand the goal, we face a real-world problem. We almost never know the true spread or standard deviation of the entire population. Because we do not know this true spread, we have to estimate it using only the data from our small sample. This extra uncertainty means we can no longer use the standard normal distribution curve. Instead, we use the student's t-distribution, which is a bit wider and flatter to account for our guessing. This ensures our mathematical conclusions remain safe and conservative. This brings us to our first major tool, the one-sample t-test formula. Conceptually, this formula measures how many adjusted standard steps our sample averages away from the claimed average. The top part finds the raw difference between our sample mean, x bar, and the claimed population mean, mu0. The bottom part is the standard error, calculated using the sample standard deviation, S, and the sample size, n. As the sample size increases, the standard error shrinks, making our test more precise, and our t-value larger if a real difference exists. Before we move on, let us see this with a concrete example. A manufacturer claims their light bulbs last 1000 hours. We test 16 bulbs and find an average of 980 hours, with a standard deviation of 40 hours. We want to know if the claim is true. We start by plugging our values into the one-sample t-test formula. Our sample mean of 980 minus the claimed 1000 goes on top. The standard deviation of 40 and sample size of 16 go on the bottom. Continuing with our calculation for the light bulb example, we subtract the averages on the top of the fraction. This gives us a raw difference of negative 20 hours, meaning our sample average is 20 hours below the claim. On the bottom, we take the square root of our sample size, 16, which gives us a clean denominator of 4. We are now ready to calculate the standard error. Remember, the standard error tells us how much we expect sample averages to naturally vary, just by random chance. This variation is our baseline for measuring the raw difference. Finally, we divide 40 by 4 in the denominator, giving us a standard error of exactly 10 hours. Dividing our raw difference of negative 20 by 10 gives us our final t-statistic of negative 2. This means our sample average is exactly 2 standard errors below the claimed average. In a t-distribution with 15 degrees of freedom, this is quite far from the center, suggesting the manufacturer's claim might be falsely inflated, as getting this result by pure chance is unlikely. So, we have successfully tested a single sample against a fixed claim. But often, we want to compare two entirely different groups to each other, like test scores from two different schools. If we can reasonably assume that the spread of scores within both schools is roughly the same, we use a method that combines their variations together. This combined variation is called the pooled variance. By pooling the data, we get a stronger, more reliable estimate of the overall spread than if we looked at each school separately. Let us look at the mathematical form of this combined spread. This is the formula for the pooled variance, denoted by the symbol SP squared. Conceptually, we are taking a weighted average of the two individual sample variances, giving more weight to the larger sample because it contains more information. The variables n1 and n2 represent the number of items in each sample, while s1 squared and s2 squared are their respective variances. The denominator represents the total degrees of freedom for this combined data. If either sample size increases, our pooled estimate becomes much more precise. Once we have calculated the pooled standard deviation, we use it to find our final test statistic. Conceptually, this formula compares the gap between the two groups to the expected random noise. The top of the fraction is simply the difference between the averages of the two samples. The bottom part calculates the combined standard error, scaling the pooled spread by the sizes of both samples. If the resulting t-value is very large positive or large negative, it means the difference between the two groups is simply too big to be just a random accident. An increase in sample size will shrink the standard error, making the test more sensitive. This formula we just saw leads us to an important question. What happens if the two groups we are comparing have completely different levels of consistency? For example, one school's scores are tightly clustered, while another's are wildly scattered. It would be mathematically wrong to pool their variances together because they do not share a common spread. In this situation, we use a special adjustment called the Welch test, which keeps the variations separate and adjusts the degrees of freedom downward to penalize us for the extra uncertainty. Here is the adjusted formula for the Welch's test, which we use when variances are unequal. Notice that we do not calculate a pooled variance at all here. Instead, we take the variance of the first sample divided by its size and add it directly to the variance of the second sample divided by its size. We then take the square root of that entire sum to get our new standard error. This approach respects the fact that each group has its own unique level of messiness. If one group is highly variable, it will naturally increase the standard error, ensuring we do not jump to false conclusions. Now that we understand independent groups, let us consider a different scenario. Sometimes our two sets of data are not independent at all, but rather directly linked pairs. Think about testing a weight loss pill where you weigh the exact same people before and after. If we treated them as separate groups, we would lose crucial information about individual changes. To solve this, we use a paired samples test, which cleverly turns a two-sample problem into a simple one-sample problem. The very first step in a paired test is to completely ignore the overall averages of the two groups. Instead, we calculate the difference, denoted by the letter D with a subscript I, for every single individual pair of data points. We subtract the first measurement, x1, from the second measurement, x2, for each person. We do this for every person in the study, creating a brand new single list of different scores to analyze. If a person's score increases, the difference is positive. If it decreases, it is negative. This isolates the exact effect of the treatment. With our new list of differences, we just run a standard one-sample test. Conceptually, we are testing if the average change is significantly different from zero. The top of the fraction compares the average of all the individual differences, d bar, to zero. We use 0 because if the treatment did absolutely nothing, the average difference should be 0. The bottom is the standard deviation of the differences, SD, divided by the square root of the number of pairs, n. This powerful method filters out natural differences between people. As the number of pairs increases, our confidence in the true effect grows. Let us apply this to a real scenario. 5 students take a typing course. We measure their speeds before and after. Because the exact same students are measured twice, we must use a paired test. We subtract the first score from the second score for each student to find their individual improvement. For the first student, 50 minus 40 gives a positive difference of 10. We repeat this simple subtraction for all 5 students to get our new data set of differences. 10, 5, 5, 10, and 5. Next, we need to find the average of these new difference scores. We add up all the individual differences, which sums to 35. Dividing this sum by the 5 students gives us an average improvement of exactly 7 words per minute. This is our sample mean, D bar, that we will test against 0. Using standard variance formulas, the standard deviation of this small list of differences turns out to be approximately 2.74. We now plug our calculated values into the paired test formula. Our average difference of 7 goes in the numerator, subtracting our expected difference of 0. Our standard deviation of 2.74 goes in the denominator, divided by the square root of our sample size, which is 5. We simplify the denominator by calculating the square root of 5, which is about 2.236. Dividing 2.74 by 2.236 gives a standard error of roughly 1.225. This means we expect the average improvement to naturally vary by about 1.2 words per minute, just by chance. Finally, we divide our actual improvement of 7 by this standard error. Our final calculated test statistic is 5.71. This is a massive number in the world of statistics, meaning the result is highly significant. We can confidently conclude that the typing course genuinely works. Let us visualize what this massive test statistic means. You are looking at a standard t-distribution curve, which represents all the possible outcomes if the typing course had zero real effect. The shaded blue areas in the tails are the critical regions. Our calculated t-statistic of 5.71 falls way out to the right, far beyond the critical threshold. This visualizes exactly why we reject the null hypothesis. Getting a result this extreme by pure chance is virtually impossible. We have covered a lot of ground today. Remember, testing means is the ultimate tool for making decisions based on limited data. We use the one sample test to check against a fixed claim, the two sample test to compare independent groups, the Welch test when variances are unequal, and the pair test for linked data. Mastering these techniques allows you to look past raw numbers and understand the true story hidden within the data. Great work today.